Okay, sorry, I just entered the Zoom meeting. So, okay, hello everyone. Welcome back to our tutorial. And our next speaker is Kashyap. The title will talk about is the specializing video diffusion model. And I will have a brief introduction of Kashyap. Kashyap is a postdoc researcher at the University of Tübingen and the Tübingen AI auto driving team, which has won multiple auto driving challenges awards from recent years. Let's welcome them.
Yeah, thank you for the introduction and thanks for giving me the opportunity to talk about some of my work here today. So my tutorial talk today is going to be about specializing video diffusion models. And I plan to cover three different things. I want to start off by giving some basic recap on latent diffusion models, specifically for videos. So I would start off by just talking about these approaches, why they work so well, and why they are kind of dominating in the field of almost all generative modeling right now. But specifically for videos, we're going to look at some of the results of the best closed source as well as open source video latent diffusion models out there. And the second part is going to be about building a model called Vista. This is a recent project we completed where we took a open source general domain diffusion model called stable video diffusion and adapted it for applications in autonomous driving. So I primarily work on research in self-driving cars, and we wanted to use these large diffusion models to help break through some of the challenges we're facing making better self-driving vehicles. So the second part is going to be about this work Vista and how we built it. And the last part is I'm going to try to discuss some of the practical tips for someone who's trying to train or fine-tune their own diffusion models, because some of these things we learned the hard way after wasting hundreds of GPU hours doing something wrong. And I thought it might be interesting to share some of the details that actually don't go into the papers, but are extremely important to train your model well. So before we get into the content, I want to quickly give a shout out to the team who worked on this project. It was a collaboration with the Shanghai AI Lab, and in particular, Shenyuan, the first author of this work, did a really, really huge amount of experiments to get us to where we are now. And so, yeah, almost all the results today are from his work. So I wanted to point that out before we go into it. Also, I'm not going to talk today about the larger vision about how we use this video diffusion model to help solve driving tasks. If you're interested in that, Hongyang actually has given some talks about it at last CVPR as well as the CCCV. So if you Google his bio, you can probably find more info on that later after the talk. All right, so let's get started. By now, probably everyone in this community, and especially the people in this room who are at a workshop on video generation, would have seen some of these demos of video generation results from the last few months. This is from the OpenAI Sora model, and you give it some text that looks like that, big blob of text, and it can generate videos that look great. They are consistent, they are long, they can be like a minute long or so. The lighting, shadows, physics all look reasonably good. Of course, there's lots of failure cases, but I would say that the rate of progress in this field is extremely rapid. The result I just showed you would not be believable to a person from 2022 or 2021 as a state-of-the-art video generation model in 2024. So how did we get here? I think the sort of key ingredient to, let me, 1 second. Never mind. Yeah, the key ingredient to getting these sort of results was latent diffusion models, also called LDMs. And they're conceptually really simple. It's not requiring a lot of technical expertise to get the idea behind these models. The first step is to build an autoencoder, which achieves some sort of perceptual compression. You have an input, which can be basically anything. People have built latent diffusion models for graphs, molecules, images, point clouds, you name it. In the example of images, let's say you have an image input and you use a 2D convolutional VAE of sorts that compresses this into a smaller latent vector. And you train this VAE completely independently in a first step of training to build this perceptually compressed latent space. Now, the main part of a latent diffusion model is a denoiser. It's a latent denoiser. Essentially, it takes a mixture of one of your latents and a certain uniformly sampled noise with the same dimension as this latent. You mix them with a certain ratio. So you could have a lot of noise and a little bit of the original latent, or a little bit of noise and a lot of the original latent. And the model's task is to predict the noise sample that was mixed into the latent. You can think of it also as a multitask model because it can perform this task for different noise levels. And the way sampling from a diffusion model works, which is really cool, is that all you need to do is train this denoiser with a very stable training objective. It's just predicting this noise. And it turns out you can start with completely uniform random noise and apply this denoiser iteratively to extract latents from your original data distribution. Once you have a latent, we had this whole step 1 where we trained a VAE. So you can use the frozen VAE decoder to get back your output, which you encoded. And if you use this entire pipeline with image VAE encoder and a lot of GPUs, you get something like stable diffusion, which can do really great text to image generation, where the diffusion model in that case is a sort of unit, and the VAE is just a very light convolutional VAE. Now, you could, of course, build a video diffusion model by making your VAE a 3D VAE. And that's what Sora does, the thing that we saw in the first video. They use a 3D CNN as this VAE. But there's another direction for building video diffusion models from image diffusion models, which is actually like much more widespread in the community, I would say, which is based on this idea called aligning your latents. Let's have a look at how that works. Now, I've visualized in an image diffusion model on this slide as of now, which I'm showing the diffusion steps from left to right. You start off with something really noisy, and you can iteratively apply this model to generate a clean latent. Now, the idea of a video LDM that uses this align your latents idea is to try to reuse your image diffusion model on a batch of latents. You want to denoise a batch of random initial noisy states. And the goal is that at the end, once you've denoised all your latent inputs, what you have are temporally consistent frames that form a sequence. So you want to give it a random batch, and make a model that can generate images that are aligned temporally and form a video together. Of course, if you just apply the standard stable diffusion model without any additional training or updating, this won't happen. If you just feed it a batch of latents, you're going to get completely independent images in the output that aren't related to each other. But the trick that you can incorporate to make this happen is add some new parameters to your image diffusion model, which are specifically designed to enforce this alignment between the image model and the eventual video model you're going to build. In this specific case, just imagine if the second element in the batch had some access to the latents from the first element in the batch. And by extension, you could have these sort of connections all the way through the diffusion model. It's possible in principle now for you to train this model to always generate coherent videos by just training it on a data set of large videos where you extract the latents that you use for your diffusion model training from a video data set instead of an image data set. And this is exactly what stable video diffusion does. It's a follow-up to stable diffusion. They build these temporal attention layers and some 3D convolutions as additional parameters on top of the image stable diffusion model. And they train this on a large data set of videos for image to video generation. So how this particular model works is you can condition it on a reference image, and given that reference image, it generates a batch of frames that are aligned to produce a video for you. Once you have this training done, applying stable video diffusion is just as simple as the single frame stable diffusion model. You start with uniform random noise in a batch, where each element of this batch represents a different frame of the video you want to generate. And over a few hundred or thousand steps of applying this denoiser, you end up with a set of outputs that match the distribution of a video, and each frame in that video sort of retains the image quality that you had when you trained your image stable diffusion model. So it's a nice way to bootstrap a video generation model from an image generation model, and has been quite successful. So I want to try to show this visually now with an example from the Align Your Latents paper. The video plays fast, so you might have to go over it a couple of times. Essentially, you will see the original stable diffusion image model generating a bunch of elements in a batch first, which are going to be misaligned. But after fine tuning, you can see the alignment emerge and you have a video at the end. So here's the first pass. And you can see at the bottom, the outputs are completely independent. And the second, you sort of have the teddy bear playing a guitar, which was the text prompt in this case. Let's have a look again. So this is the first pass. They're all different images because they're different elements in the batch. And after aligning the latents, you can generate a video. And the important thing is in this alignment process, you freeze all the parameters of the original model and only add new parameters for this temporal alignment. So it doesn't take as long to train as a video diffusion model from scratch, right? So that was my recap on stable video diffusion, and we did see some results. It looked quite interesting, but what we were interested in is, can you take this open model? So stable video diffusion has open code and weights and quite a permissive license on what you can do with it. So can we take this and use this to solve some of the challenges we face in building better autonomous driving policies? And for this, we found out that using stable video diffusion out of the box isn't great. I'll talk a bit about why. And so we tried to specialize it in the way we needed it to solve our problems. Now, what I talk about here is going to be some problems specific to driving and how we specialized it for that. But I think most cases of doing domain-specific applications could benefit a lot from the type of problems we faced and the knowledge of how we fixed them. So I do think some of this information is relevant also if you're trying to apply video diffusion models for robotics or like other broader application domains than driving. So let's look at some of the problems. I told you that SVD is a image to video model that can condition its outputs on a reference image. Here's an example of a video generated from SVD when you condition on the frame on the left. And you can see that even though a lot of elements from the condition frame are incorporated in the generated video, there's actually no constraint on this model to use the condition frame exactly in that form in the video it generates. So you have an initial frame of the video that was generated that has the same clouds and sort of the same highway layout, but it's completely missing this signboard, which may be important for your application. And so this is one reason you can't really use this model autoregressively, because it can't obey or it can't stay consistent to the condition frame, which means that if you try to apply it with its fixed generation output length multiple times, so you kind of feed its output back as the condition and try to reuse it, you're going to end up in the situation where your video quickly diverges from the condition. And this is what that looks like. We tried to apply it for 15 seconds. This model generates 2.5 seconds of video at a time. So this is 6 applications of SVD. And you can see by the time we get to the end, it's almost unrecognizable in comparison to the original scene we started off with. And long applications of video generation are quite important, I would say, in many domains. So one of our goals with Vista is to try to solve this problem, try to enable autoregressive use of the stable video diffusion model. And we did achieve that. This is just like a sneak peek into our results. So this is kind of what you want. And this is what we achieved after some fine tuning. So you now get the ability to roll out this model for at least 15 seconds. It is unstable beyond that, but this was something that made it much more useful. So how do we do this? Like, obviously, like our first hypothesis was the model is just not trained on a lot of driving data. We probably need to specialize it a bit to the driving domain. So let's go ahead and train this model on some driving specific data. But the funny thing is, the data sets we actually have in autonomous driving are not that diverse or large in comparison to the data sets that the base SVD model was trained on. So this is from a data set called NuPlan, which is already, I would say, the largest and most diverse public autonomous driving data set, at least with a lot of labels, and it's widely used in the driving community. But the data set only covers 4 cities, and it has a lot of very similar looking scenes. I tried to just randomly sample some scenes here, and you can still see a lot of them have a camera in exactly the same position with similar lighting. It's all very clear, and your similar typical gray street with lots of buildings in the background. And there has been prior work that tries to specialize SVD or any video diffusion model using this sort of driving data set, but they always become too specialized in the sense that you can then only apply them on this data set, and they're no longer useful for other driving data sets even, because the diversity is so low if you only train on this kind of data. So how do we fix this? Well, we use the internet to come to our rescue. I found this stat, which is like, it was honestly quite shocking, but every minute there's 500 new hours of video uploaded to YouTube. That's a factor of 30,000. So there's 30,000 minutes of new uploaded video by users on YouTube for every new minute that passes in the world. And this is a stat from 2022. So I'm pretty sure 2 years down the line, this has only gotten much, much more. And believe it or not, there is a huge amount of driving videos on YouTube. So there's a lot of YouTubers who just put up professional cameras on their cars and drive around and take hour-long videos in their own cities at different times with a lot of diversity. So we managed to collect this data set from YouTube clips, which we call OpenDB2K, and we released it. This was part of an earlier work before Vista. And this is, I think until date, the largest publicly available driving data set for driving videos. It has 2000 hours of driving, which amounts to 65 million frames. That's 65 times larger than ImageNet roughly. And it's really diverse. So I talked about the previous Nuplan data set being from 4 cities. We have now 700 cities in this data set represented, and it really gives you this scale and diversity that you need for specializing the diffusion model to this new domain. So that was the first ingredient. We got our data, we grabbed it from YouTube. Let's see what's next. Even with this data, we had a lot of bad initial results by just fine-tuning on it with the exact SVD architecture. And we kind of realized that one of the biggest problems was, given a single reference image, the fine-tuned model on the driving data couldn't decide whether to make the other cars speed up or slow down over the video. So there's some situations where there's car in front of you that's accelerating and increasing its pace. And there's some where it's coming closer to you because you are moving faster. And we kind of realized that this problem is because we condition on only a single image. So if you look at this architecture layout, which is just a copy of what I showed a few slides ago, when you're trying to denoise this particular frame, in the initial steps of denoising, the SVD architecture actually has access to only a lot of noise about the previous frames. And this makes it really difficult for it to stay consistent and roll things out autoregressively. But what we did is actually a quite simple idea. We replaced the noisy inputs of stable video diffusion with clean latents randomly, sometimes during training. So it's kind of the opposite of dropout. In dropout, you take things out to improve robustness to the model. But here, we took a really hard task of denoising high noise levels and sometimes leaked in information of the acceleration and the speed of different things in the scene that help the model become more consistent. And in practice, this is as simple as dropping a specific line of code with some probability in your training loop, where you sometimes let in clean latents to the input of different token lengths. And you can use this model the exact same way as the previous SVD model. But the interesting thing is now you can condition it on multiple frames when you roll out autoregressively. You can generate a video and you can maybe use the last 3 frames or the last 4 frames of your generated video as the input to the model again, rather than just one, which was the only thing you could do with the base model. So using this, this is the key ingredient of basically getting these long rollouts. You use a really diverse data set, you give it a bit more conditioning, and compared to all of the other driving video generation models out there, this was the first one that really could go at a high frequency, so 10 hertz of video resolution, a high image resolution, so HD resolution images, and for long durations of 15 seconds. So we could stop at this, and there's already a lot of applications you can do in driving with a long unconditional video generator. But something else we wanted to do is add some controllability into the video generation. So the typical SVD only gives you this reference frame to condition the image on. And in an application like driving, you maybe want to imagine what would happen under lots of different conditions. And here I've sort of replace the same figure, like this is the figure from the paper of what we have before. We have this replacement. This is just illustrating that we condition now on multiple frames and pass it through this Vista model autoregressively to get a really long future. But a second modification to kind of make this model much more useful is adding action controls. And we also do this with a very simple trick. We add a bunch of projection layers that go exactly in line with the conditioning that's already implemented in SVD. So where you have this reference frame and the image conditioning, we expand that with slightly more information, which is encodings of different types of controls. And I'm not going to get into the specifics here, but the important part is that it's really easy to initialize these layers such that they have no impact on the output of the model. So you do a sort of zero projection that lets you add these layers into the network without actually changing its behavior at all at initialization. And you can now fine tune it with a certain amount of data where you have the control and video pairs. This isn't available on YouTube, but it's available on a lot of driving data sets, and we'll see later how exactly we did this. But I just wanted to show the slide to kind of give a hint at what sort of results you get once you apply a bit more fine tuning. So this is a second level of fine tuning. We first did something to let us generate long rollouts and driving videos. And then the second step was making it controllable, where you can give it different commands. You can also give it steering actions, give it these waypoints, which are positions where you want the car to go. And you get out different videos that follow these commands like this. Here's just another example. And of course, the results aren't perfect, but there's already a lot you can do with this model. So as I said in the beginning, if you're more interested in how we use this model, there's a nice talk from Hangyang at CVPR, which you can check out later. So on to the last and longest part of this tutorial talk, which I'm also most excited to be talking about, is some of the practical tips and some of the sort of dark knowledge that you gain by working with these models, but never really see when you just read the papers. So specifically, I'm going to talk about some of the things we figured out while training this model that were quite interesting to us. All right, so what's the most important thing during training was my question on the previous slide, and the TLDR simple answer is a lot of GPUs. You need to use a lot of resources to train these models to get good results. But the funny thing is, just having a lot of resources is enough. You actually need to use them smartly as well. And that is something we maybe learned the hard way by wasting a lot of GPU hours. But hopefully you now have the information and won't do the same thing as us. So I want to start by talking about a weird trick that people used in diffusion models for around the last 2 years. Like it started with a particular diffusion model and it was never explained. And that's the exponential moving average trick. So way back in the Adam paper from 2017, there was this hypothetical future extension section called temporal averaging. And this was the only explanation I found after like discussing with the authors and looking through threads on why EMA is actually used, exponential moving average is actually used in diffusion models. So it seems that for a lot of applications, when you train your model, the model overfits to the very last few batches it sees during training. So it turns out that for certain types of training, they are much more stochastic than others with respect to this particular characteristic. And it's especially high for diffusion models, to the point that the solution that people came up with is keeping a moving average of weights throughout training. So you choose a factor like 0.9 or 0.99, and you start with a copy of your initial weights that you're training with SGD or Adam, and a second set of weights, which are also on your GPU, but initialized to be 0. And every training iteration, you take a moving average by averaging in your SGD or Adam weights into this initial 0 weight snapshot. And you do this over training. And this has apparently been something people have been doing since 1992, but I've seen it used most frequently in domains where training seems to be more unstable, like reinforcement learning. But surprisingly, it's really important for diffusion models, which are typically considered to be stable to train and quite easy to train without diverging. And a question arises like, if it just works, why would you even think about it? Why not just use it? It seems like a simple trick. Well, there is a disadvantage of using EMA, and you only kind of see it when you start working with these huge, humongous models. The EMA trick requires you to store a second copy of your network parameters on GPU. So it's really slow to do a per iteration copy of all your parameters from your GPU to your CPU, and then update this EMA model on your CPU or disk. So the only way to do it effectively is to have two copies of your network parameters on your GPU and do the moving average every step. But this uses a lot of your GPU memory when you're using a really big model. So here is like the specific details of what happened in our training. We train our model on this YouTube data set from the slide I showed earlier for a long time. So we train it for 8 days on over 100 A100s. But in this particular stage, when we were first changing the domain, we found it really important to train all of the unit parameters. And this is 1.7 billion parameters. These parameters occupy 11 GB of memory on each GPU, which is around 15 or 10 to 15% of the entire memory you have available for training, which you use for this trick. We thought we could remove this because one of our problems was the entire model didn't fit on an 80 GB A100, and we were trying to find ways to reduce memory consumption so that we could at least fit a batch size of 1 onto one 80 GB GPU. But we found that we can do that by removing the CMA trick, but the model just gets worse over training. It starts off really good, and the more driving data you train it on, the worse it gets at predicting driving videos. And this was kind of like one of the more surprising results to us, that without the CMA trick, diffusion models don't really train well at all. And people don't explicitly say this. It's just that the EMA code is just copied over through all the repositories and reused over and over. So with EMA, how do we train? Like I said, like a batch size of 1 doesn't fit on the GPU. So we need to do gradient accumulation. This is a trick where you don't do an entire forward pass and store all the activations of your model while training, but you rather do a partial forward pass. And while computing your backward pass, you redo some of the forward operations. And this is not convenient. It slows down the training a lot. But since we needed the EMA, we also needed the gradient accumulation to actually make the model train. So this was the first little anecdote from some of our early runs training this model. The next one, which also has an interesting source, is something called offset noise. So a few months ago, or like by now it's like a lot of months ago, there was this blog post that came out about diffusion with offset noise, where they discuss a very weird and specific problem with diffusion models. Because these models are trained with a data set that is collected by adding noise to real data, there's a shortcut that these models can learn that makes them really bad at generating very dark or very bright images. I'll try to kind of summarize why this happens. If you imagine a very bright image, even when you add a lot of noise to it in the forward diffusion process to make this highly noisy input, that is the first input of your diffusion model for denoising, it turns out that the noise functions we use aren't very good at changing the mean of the entire image. So if you start off with a very bright image, you get a very high mean value after adding a lot of noise. And if you start off with a very dark image, you get a very low mean value. And the diffusion model learns this shortcut where it kind of copies the mean of the noisy input it sees to set the brightness of the output it sees. So it's kind of exploiting the shortcut of using the information that was leaked in its input to generate an output with a similar brightness level. And what happens during inference when you deploy these diffusion models is that you always start off with zero mean noise. So you start off with a model that has a zero mean. And even if you give it a prompt saying like a very, very, very bright image that people try to do, it just can't generate images beyond a certain brightness. And the fix to this, which was proposed in this blog post, was to also noise the entire image with a small secondary noise component. So you have your regular diffusion noise, which you apply per pixel with a different Gaussian sample, but you also sample a small secondary noise term. In this blog, they used 10% of the strength of the regular noise. And this is uniformly applied to all pixels to change sort of the mean of the entire image while denoising. And this trick worked quite well and has been used in some niche applications for artists when they try to generate really dark or really bright images. Now, the interesting thing we found is that the offset noise trick is also super useful for video models to make them more consistent to their video inputs. We don't have rigorous experiments on this because this was considered like not novel enough to put a lot of emphasis in the paper because some people know about it and have been using it. So we just mentioned that we use this trick. But the way that we hypothesize this works, and like my results here try to show that, on the top left of each block, the first two frames are the input reference frames. So it's these two in this case, these two here, and so on. And the top rows are the results of generating 6 frames with these reference without the offset noise. So this is our baseline where we don't use the offset noise. And we see that the output of this model is like really quickly diverging again from the references. Whereas the bottom rows are for when we do add this offset noise. You can see here that, for example, the color of the sky stays much more consistent for the next 6 frames. And on the bottom, the background actually stays sort of sky, as opposed to here, the background eventually kind of morphs into a mountain as well. And these are like really preliminary experiments for training from scratch. So I don't have results for this on the final model, but I just wanted to give a hint of how it works. And the hypothesis we have of why this helps so much is that similar to the dark and light image case, the video model actually has more information in the like partially noised inputs because you can't destroy all the low frequency information while denoising when you don't use this offset noise, which makes it able to use a shortcut that lets it not refer to the reference images as often for generating the mean of its output. And once we do add this trick, it improves the results a lot. So that was the second trick. The third one is about loss weights. So we put a lot of effort into trying to tweak the architecture to better suit our like intuitions about how driving works and make the model better at generating driving videos. But in the end, the more effective trick we found was actually tuning the losses. And this can be really simple. We just use the diffusion loss as it is, but we identified some weights that increase the diffusion loss at certain pixels, which we found had the highest amount of errors. So one thing we saw is that the model by default likes to keep scenes static. So it has seen a lot of static things and it doesn't like to move things at high speeds. But you do have things moving at high speeds in driving scenes. And so some of the effects of a baseline model are that the car in front in this case actually doesn't move very fast at all. It like you almost always had cars in front of you slowing down in all the generated videos. And on the right, this is a bit hard to see, but the white dotted line is kind of showing a particular reference point along the road where you can see the trees end here and the sky begins here. And what we did is we actually generated a video where the car swerves right. And even though the car visibly swerves right at the beginning of the video, which you see, the background actually stays in the exact same place. So you'd expect the trees to move to the left if the car moves right, and that doesn't happen. We also have these weird, bad structures which are blurry when you have certain details in the image. And we do a couple of simple fixes for this failures that we observed. We increased the weight of moving regions in our loss by essentially measuring something like the error of the optical flow in the latents. So we took ground truth latents and took their difference. You can think of this as the optical flow of the ground truth latents. And we took the generated latents from the diffusion model, that's the term on the left, and also generated the difference. So you have two sort of optical flow terms. You take the difference, the error between them, and you sort of get a heat map of all the moving things in the image. And using this trick, we can easily upweight the diffusion loss on these pixels. And this really helped us generate diverse motions in our data set. The second thing was for these like boundaries of objects. We also wanted to increase the weight explicitly there. Here we used the Fourier transform and the inverse Fourier transform and did a sort of high pass filter. That's this H thing that selects the samples that basically have a lot of high frequency detail in them. And we also added a higher weight for these portions of the losses. And these sort of tricks, I think, can be generalized to apply your intuitions of what failures you care about, convert them into a loss weight, and make the model better at predicting those particular things. These are some of our results once we did apply these loss weights. So you can see on the left, the car in front does move naturally in the speed it was going at before. And in the second one, as the car swerves a bit to the right, you can see the tree line moving to the left. We also fix some of the blurry frequency artifacts that you have on the right side here. All right, and this is my last point. We did a lot of experiments on how to scale the diffusion model, like as we added parameters. Do we add more parameters? Do we increase the batch size? Do we increase the training time? And I told you about this first training phase where we spent a lot of resources and kind of got our base model. The results I showed earlier of how to make the model controllable actually were done in a more intricate training, which required much less resources. So in the second training phase, because we needed the labels of how the car moves, we needed to mix in our YouTube data with some data where we have that labels. We used a data set called new scenes for this, which is much smaller, but actually has these commands of like stop, turn left, turn right labeled in the data set, along with some other action modes that we want to control by. The interesting thing we found is that when you just want to add conditioning to the model, you don't need to start from scratch and train with all of your resources on the entire data set. You can actually learn conditioning with much fewer resources comparatively. So we used only 8 A100s as opposed to 128 for learning the conditioning and making this model follow instructions. The most interesting thing, I think, is that even though we wanted to generate videos at this resolution, 576 by 1024, we could actually spend a huge amount of our training budget, so 80% of our training time, training at a much lower resolution than the one we cared about. So we use the exact same model. We just feed it smaller inputs and it generates smaller outputs for a significant portion of the training time for this model. And this has a couple of effects. It lets you use a bigger batch size and it lets you get more iterations per second. And we also really carefully disentangle the effect of these two things to see why it was so much more effective to train at a low resolution. And we found out something interesting that for diffusion models, increasing the batch size doesn't actually speed up convergence. this is like your common intuition with training a machine learning algorithm is that if you have a bigger batch size, you have less noisy gradients, and with more resources, you can converge faster. But in terms of wall clock time, we saw that increasing the batch size was actually making the model converge slower in the case of second stage of diffusion training. It wasn't becoming controllable as quickly. So if we just wanted to train it as fast as possible, it would be better to use a small batch size. But what does help a lot, and what seems to be the most important factor to scale for any diffusion project, I've also seen this in other projects, is try to get as many iterations per second of training of your model done. You can do this by using smaller models. Unintuitively, it's sometimes better to use a smaller than a bigger model for diffusion just because you get more iterations per second. And we also saw this over our projects where using Stable Diffusion 1.5, a smaller model was better than Stable Diffusion XL, or use a lower resolution image. And you can do a lot of training at lower resolution images or videos, and then only do a little bit of training at the high resolution, but still have the positive effects of using the high resolution as if you did it the whole training stage. All right, so this is sort of the end. I wanted to sort of summarize these practical tips. So this EMA trick of having a running average of your weights has a really big memory overhead when you use large models, but it seems to be essential. So maybe there's something to look into there of why that's happening and how it can be done better. Maybe it could only be applied over the last few iterations or epochs of training, for example, and that lets you use more of your GPUs early on in training. The second point is that this offset noise trick that people used in generating high contrast images is also very useful for video generation. Tuning your weights can be quite necessary in some cases to make your model overcome certain failure modes. And if you are limited on resources, the thing that you need to try to scale is the throughput of your training. So how many iterations per second you run through. All right, so the model I showed you is completely open. We've opened the code and weights, and the QR code here gives you access to our code. Also, the website has a lot of nice demos, and I should have a video here, but YouTube is dying on me. So I downloaded it, and hopefully I can show you some results of how generated videos look like. So that's it from my side. Happy to answer any questions as best as I can. Thanks.
On the report, and due to time limits, we have only one question. No more question. I have one question. As the development of DIT-based model, they have generated better videos in many aspects. So one question is, would these techniques fail when the SVG works with these techniques? Maybe it will fail based on the DIT-based model.
I-
They have such as because they have the full attention to modeling both spatial and temporal dimension.
So I think obviously not all of the techniques I talked about would be applicable for a DIT type model. Some of them rely on this like two-stage interleaving, but conceptually I like the DIT based models much more. They're simpler and more scalable. The problem is just there aren't any good open source ones. So I think like if we had a open DIT based video model, we would have done this whole project with a DIT based model. That's the short answer. Yeah. Now, yeah, so that's good to have. Oh, thank you.
Thank you.